Hi, my name is Nurullah Erinola, and today I give a talk about our paper Exploring the Unknown DTLS Universe, Analysis of the DTLS Server Ecosystem on the Internet, which is a joint work with Marcel Maehren, Merget, Juraj Somorovsky, and Jörg Schwenk. DTLS is the datagram transport layer security protocol and an extended variant of the TLS protocol that can be used to secure unreliable connections like UDP. It brings the same security guarantees as TLS and is mostly used for latency-sensitive applications such as VPN, voice over IP, video conferencing, and online gaming. As in TLS, a client and server perform a handshake to negotiate cryptographic parameters and establish a secure data channel. Then they can exchange encrypted application data via a secure data channel. To work over UDP, DTLS makes minimal changes on TLS and addresses different problems. Let's take a closer look at this. The first challenge is the unreliable transport. Messages can be lost or reordered. DTLS solves this by adding a simple retransmission mechanism. Both peers maintain a timer and retransmit when the timer expires. The second challenge are denial of service issues. An attacker can consume excessive resources on a server by sending a series of handshake initiation requests, for example, client hello messages. Furthermore, amplification issues are also a challenge. An attacker can use a server as an amplifier by sending connection initiation requests with a spoofed IP address. To counter attacks like this, DTLS introduces a stateless anti-DOS cookie exchange. When a client sends its initial handshake message, the server can respond with a cookie that the client must replay. The last challenge is the maximum transmission unit. In TLS or DTLS, handshake messages can be very large, for example, the certificate message. In TLS, the TCP protocol fragments large messages automatically. Since UDP does not offer such features, DTLS must do it itself. We see that DTLS introduces many new features to address different problems. But it is unclear if these new features open new vulnerabilities unique to DTLS implementations. In previous work, we cannot find an accurate answer to this question. They have intensively studied the TLS ecosystem, but not the DTLS ecosystem. To fill this gap, in our work, we considered known attacks on TLS and analyzed DTLS IRCs to identify DTLS-specific features and possible vulnerabilities. We then created a security catalog of threats and security pitfalls for DTLS implementations and used them to evaluate open source server implementations in the lab and publicly available servers on the internet. In total, we created 17 DTLS-specific tests. Our tests can be divided into 4 groups. Let's take a closer look at this. First, we have the category cookie exchange. It contains 8 tests regarding the optional anti-DOS cookie exchange. For example, we check if the server issues an anti-DOS cookie or if the server validates a received anti-DOS cookie. Secondly, we have the category retransmissions. It contains 2 tests that check if retransmissions are correctly processed or sent. Thirdly, we have the category fragmentation, which contains 4 tests. Here we check if the server supports fragmentation and if the fragmentation feature of an implementation offers possible denial of service vulnerabilities. Lastly, we have 3 tests that test different small features, for example, reordering. We implemented all these tests in TLS-Scanner, which is available on GitHub. It is an open source scanner for black box evaluation of TLS servers. It automatically scans a TLS server and provides a report of supported features like protocol versions, cipher suites, extensions, and potential security issues. We first added generic DTLS support to scan DTLS servers and then integrated our DTLS-specific tests. Okay, let's now take a look at the results of our evaluation. We first used the extended TLS scanner to perform a lab-based evaluation of 12 open source DTLS server implementations, for example, OpenSSL. On the left side, we now see all 17 tests implemented. Due to time constraints, I would like to summarize our most important findings. The most critical vulnerability was the plain check injection vulnerability in one of the tiny DTLS variants that allows an attacker to inject application data at any point once a handshake between 2 peers has been completed. Further, we detected amplification vulnerabilities in 3 libraries. JSSE, Scandium, and wolfSSL, where the servers can be used as amplifiers by abusing the session resumption feature of TLS. We also identified 5 memory execution vulnerabilities. We could force the servers to create a per-client state before an anti-DOS cookie has been exchanged by sending fragmented initial messages, for example, fragmented client hello messages. Finally, we observed that matrix SSL crashes after receiving unexpected messages, for example, an encrypted finished message. After the evaluation of the software libraries, we proceeded to scan available DTLS servers on the internet. However, that was not so easy. For TLS, it is simple. Mostly the TLS stack of web servers was analyzed on port 443. For DTLS, it is unknown on which ports it is mostly deployed, and it's unknown which services actually use DTLS. To answer these questions and find DTLS servers on the internet, we use ZapMap, a network scanner, in a 3-step approach. Let's take a closer look at this. In the first step, we did a pre-scan of 2^17 random IPv4 addresses on every port. In the second step, we increased our sample size to 2^20 for each port where we discovered at least one DTLS host. In step 3, we choose the 8 ports with the highest number of responses to scan the whole IPv4 range. On the right side now, we can see the result of our approach. On port 443 and 10443, we found most hosts speaking DTLS with about 270 and 260,000 hosts. In total, we found more than 600,000 hosts. However, we have evaluated only 78% of the hosts. This is mainly due to 2 reasons. A server did not respond after some time, for example, due to blocking, or bugs in the DTLS implementation prevented a server from completing the DTLS handshake with our scanner. Now, let's look at what kind of services we found and evaluated. We tried to identify the service over the server's response after sending messages from different application protocols. The distribution of the identified services now we can see on this figure. We detected a VPN application from Fortinet as the most popular service, followed by Cisco's WAN management tool called VoIP. We also found stun and ton services, but they only make a small fraction on port 443. Okay, let's now analyze the DTLS configurations. We collected the supported protocol versions, cipher suites, compression algorithms, and elliptic curves, and more to analyze if obsolete and insecure algorithms are still in use. Due to time constraints, I would like to summarize our findings regarding the key exchange and followed by the encryption algorithms. We found that the elliptic curve Diffie-Hellman imperial and RSA key exchange is preferred over the classical Diffie-Hellman imperial key exchange. We also checked for Bleichenbacher and invalid curve vulnerabilities and found that they are mitigated in the DTLS ecosystem. We also checked for weak RSA and Diffie-Hellman cipher suites, for example, for export cipher suites, to identify possible logjam and freak vulnerabilities. We did not find any. Now we see the supported encryption algorithms. We noticed that 13% of the hosts accept at least one cipher suite with null encryption, which does not achieve confidentiality. We also detected that almost all hosts on one port, 1106, supported RC4, the RC4 stream cipher. It is interesting because stream ciphers are forbidden in DTLS due to the unreadable connection. In addition, we identified that 16% of the servers supported the triple DES encryption scheme, making them potentially vulnerable to the Suite 32 attack. However, the support only poses a real threat if it gets negotiated and are used to transmit large amounts of data. Finally, regarding the supported block ciphers, we also checked for padding oracle vulnerabilities and found 472 observable padding oracles. Okay, let's now take a closer look at the DTLS-specific properties. Due to time constraints, I would like to summarize our most important 3 findings. On port 443, 13.5% of the servers did not validate the received anti-DOS cookie and accepted random cookies, which allows an attacker to use these servers as amplifiers. We were able to measure an amplification factor up to 32. In addition, we identified that there is partly a lack of support for fragmentation and reordering, which influences the stability and interoperability of an implementation. Almost all servers on 3 ports do not support both features. Lastly, we observed that almost all servers on 5 ports do not implement a retransmission timer and only send retransmissions themselves when they receive retransmissions from the client. Okay, let's come to the conclusion. In our work, we created a security catalog of threats and security pitfalls for DTLS and evaluated open source server implementations and publicly available servers on the internet. We published the first comprehensive dataset on DTLS servers and opened the DTLS ecosystem to the community. All details can be found in our paper. Furthermore, the extended TLS-Scanner can be found on GitHub and can be used for the analysis of DTLS server implementations. We identified unsupported DTLS-specific features like fragmentation and reordering that influences stability and interoperability of a DTLS implementation with other implementations. The respective vendors must take improvement in these areas. Finally, we identified that the DTLS-specific features can open new possible vulnerabilities unique to DTLS implementations. We found that denial of service and amplification attacks are a threat for DTLS implementations. But we also found that the known TLS vulnerabilities in the DTLS ecosystem have been mitigated. Thank you for your attention.